In this concluding lecture on special beam applications, a practice problem on a beam with an internal hinge shall be undertaken, the answer key of which shall be discussed subsequently. The beam for practice is shown here in this slide. The two parts of the beam, namely ABC and CDE, are connected together at C by an internal hinge or bending moment release. The given beam differs from the beams in the solved problems in that a point load of 12 kilonewtons acts directly over the internal hinge, and this makes the problem somewhat confusing. You may wish to use a hint to solve the given problem by assuming either the entire 12 kilonewton load to be acting at C for the part ABC and nothing at C for the part CDE when the two beam parts are analyzed separately, or the entire 12 kilonewton load to be acting at C for the part CDE and nothing at C for the part ABC when the two beam parts are analyzed separately, or a part of 12 kilonewtons, say 6 kilonewton to be acting at C for the part ABC and another 6 kilonewton at C for the part CDE when the two beam parts are analyzed separately, or distributing 12 kilonewtons load in different proportions for each part when analyzed separately, but the total load at C sums to 12 kilonewtons when both parts are joined together. In all the possibilities of analysis described in the hint, we shall eventually end up with a unique solution. You may pause the video at this juncture, solve the given problem using one or many of the hints described, and resume the video for the answer key. Welcome back to the answer key to the given practice problem. Let's apply the first hint. The two parts of the beam are separated and the loads are shown with the assumption that the part ABC holds the entire 12 kilonewtons at C, while the part CDE does not hold any load at C. The shear force diagram and bending moment diagram shall be obtained as shown. If we apply the second hint, then the entire 12 kilonewton load is shown acting at C for the part CDE and nothing at C for the part ABC. Analyzing, we observe that we end up with the same result as obtained from the first assumption. Now, let's try with our third assumption, that is 6 kilonewtons acting at C, each for part ABC and part CDE, and we find that it leads us to the same result obtained earlier. Finally, we may try out innumerable combinations of the loads acting at C for either part, making sure that the summation of the loads assumed at point C for both the parts in either case leads us to the same value of 12 kilonewtons. We find that all different combinations lead to the same unique result. From this practice example, we conclude that there is no specific way of distributing the given load at the internal hinge when we separate the beam for analysis. This nature can be explained from the loading diagram for the part CDE, which resembles a simply supported beam. Whatever load we add at point C, be it 0 kilonewtons or 6 kilonewtons or 12 kilonewtons or any other value when the beam is separated at internal hinge C, does not contribute to the reaction at E in any way. Recalling from our earlier lecture for a simply supported beam with an eccentric point load, the reaction at the right support equals P times A over L, and here the proportion of load added at the internal hinge has the value of A as 0. Hence the reaction at the right support remains unchanged. We hereby conclude our discussion on the axial force, shear force and bending moment in beams and in special beam applications. We start with a new topic in the next lecture, namely the theory of simple or pure bending or flexure.